Okay, because they are requests. Sorry for that. I just start recording. Okay. Okay. May I ask, is it for V line and I line, the unit is RMS or RMS? So usually it will inform you whether it is RMS or RMS or not RMS. Okay. As mentioned before during our previous class, you can ask the lecturer or the invigilator whether it is RMS or maximum value. Usually it is, it depends because some of the lecturers, because they refer to other books. Okay, for example, for the Sadiku, our textbook, it use I think RMS, but there are also another book that use maximum values. So several of the lecturers, they use different books. Okay, because for this course SEE2423, we have several textbooks. Okay, so that's why always you can ask the invigilator to confirm whether it is RMS or maximum. Okay. Yeah. Okay, so for example 6, did I answer your questions? Because this is just a straightforward. Okay, just a straightforward. Okay. Okay. So this one, okay. Example 7. Okay, example 7. Which one example 7? Okay, this one. Okay, so example 7. A balanced ABC sequence Y connected source with VAN. Okay, so right now your source is Y connection and your delta is, your load is okay, and the load is actually delta. Okay, and the load as mentioned here, each phase is actually with a value 8 plus J4 ohm per phase. So determine the phase and line current, sketch the phasor diagram at the load. So there are questions. Oh, did example 7 and 8 no solution? No solution in the e-learning. Okay. Okay, so I will upload it. Okay, as soon as possible. So determine the phase and line current. So this is actually referring to the load. Okay, usually when it required you to determine the phase and line current, so it is always referring to the load side. Okay, so meaning that determine the phase and line current for the load and sketch the phasor diagram at the load. Okay, so right now the source is VAN Y connected. Okay, and then it is actually a positive sequence. Okay, so your VAN is given 100 angle 10 degrees. So this is your reference. So your reference angle is 10. So meaning that all your VBN, V phase must be referring to this reference. Okay. So instead of starting at 0, so your reference start at 10 degrees. So your VBN must be with an angle of negative 110 and your VCN is 130 degrees. So actually it doesn't matter because because if I plot the phasor, okay, For example, this one, VAN, 10 degrees. And then my VBN will be negative 110. So this one. So this is my VAN. This is my VBN. And my VCN is 130 degrees positive. So this one. Okay. So if you look, the difference is still the same. So this is 10 degrees. So this is 130 degrees. So but the difference is still 120 degrees. This one also 120 degrees. This one also 120 degrees. But the only difference is actually it start at 10 degrees. So VN start at 10. So meaning that you need to shift all the phase voltage shifted to 10 degrees. Okay. So this one will become negative 110 and VCN is 130 degrees. So this is actually at the supply side. So at the load side, we know that the delta, the V phase and V line is actually not equals. So you need to convert the phase voltage into a line voltage. Okay. So right now your VAB is square root 3 of the V phase, which is your VAN, and you need to with an angle of 30 degrees. So right now your VAN is 100 with an angle of 10. Okay, so meaning that 100 multiplied with square root 3, so 173. And the angle is 10 plus 30, so your VAB is 40 degrees. Okay. And also for VBC, so square root 3 multiplied with 100. Okay. And then the angle from the VBN is negative 1110. So just plus 30 degrees. So that's why you have negative 80 degrees. Okay, this one is actually come from negative 1110 plus 30 degrees. Because your VBN is 100 with an angle of negative 110. Okay, so and also for the VCA. So meaning that if I plot my V phase, okay, my V line, which color that I, okay. So my V line, so V line will be always, for example, this one is your VAB, okay, 30 degrees. My VBC also 30 degrees leading, and also this one is actually my VCA, also 30 degrees. Okay, I think this one negative 80, okay? Okay, so I think this one is at here, okay? So blah, okay, 30 degrees difference. Okay, so actually the magnitude should be the same lah, 170 degrees as 173 volt. Okay, so as you can see, if I plot here the phasor, the V line will always leading the V phase by 30 degrees. Okay, so VAB leading VAN, VBC will leading the VBN, and VCA will lead the VCN. So if the rotation is like this, okay, counterclockwise, the rotation. Okay. For the phase current, so delta, I line and I phase is actually not equal. So you have the IAB here. Okay, IAB. So this one phase current, okay, IAB here. Okay, so VAB is equals, sorry, IAB is equals to VAB, the V phase over the impedance of the phase, ZA. Okay, so you will obtain the values IAB 19.3, with an angle of 13.4. So since the load is balanced, so the magnitude will be always the same. So for IBC also same. The only difference is actually on the angle. So IAB and IBC will be always 120 degrees different. So meaning that to get these values, 106.10. So what you do is negative 120 degrees plus 13.4 degrees. So you obtain negative 106. And also for ICA is 120 plus 13.4 degrees. Okay. So this one, I think I will post in the WhatsApp group. I think I have already sent it. I don't know. Okay, sorry. So this one question, determine the phase and line current, meaning that for both, okay, sorry, for both, for the source and also for the load, okay. So the source right now, it give you the value of V phase, okay, 110. So from that VAN, you can obtain directly your VBN and also your VCN, okay, for the source. Okay, and from that also, since we know that for the Y connection, V line is not equals to V phase, so you need to calculate your V line, which is your VAB here. As you can see, VAB is actually from line A to B, so you need to calculate based on the equation here. So you will obtain your VABs and so on. Okay, and to calculate your phase current, IAB, this one is your phase current. So right now at the load side, you have IA, IB, and also IC. Okay, IA, IB, and IC is I line, while IAB, that current that flow from this node to this node, is actually IAB, and this IAB is your V phase. So to calculate your IAB, is actually you need to obtain the voltage across the impedance. Okay, so right now the voltage across the impedance is this voltage, which is VAB. Okay, and the impedance is ZA. So that's why for IAB, I calculate by using this formula. Okay, and IAB is your I phase. And after you obtain the I phase, then after that you can obtain the I line, where I line is actually square root 3 multiply with I phase, and the angle should be minus 30 degrees. Okay, so for this case, for example, if I have obtained my IAB 19.3, 13.4, so this is my phase current. So my line current IA is square root 3 multiply with 19.3 angle 13.4 minus 30 degrees. Okay, because the line current will always lagging the phase current. So that's why I obtain my line current is equals to 33.4 with an angle of negative 16.6. And then for IB, since this is the load a balance system, so the value is still the same, but this one is 16.6. You need to minus 120 degrees. Okay, because because between this IA, IB, and IC, there will always a displacement angle 120 degrees. So my IB, I will obtain negative 36.6, and my IC is actually same, magnitude 33.4, with an angle of negative 16.6. Sorry. Okay, plus 120 degrees. So that's why I obtain this one is around 103.4. Okay. I don't know this one might be wrong, but should be like this. So 120 minus 16.6. So yeah, 103.4. So, polar form without writing RMS. What do you mean by that? May I ask, we leave the final answer as polar form without writing VRMS. What question that you referring to? So this one, okay, you can just leave it like this, no problem at all. In polar form. Okay. So anything else? So this is actually for the balance system. Okay. So the balance system, they always using the relationship between the I phase and I phase, V phase, I line, and V line. Okay. So okay, and then for the unbalanced system, is there any questions for the unbalanced system? Or you haven't yet go through the notes? For the unbalanced system. Unbalanced system, example 7 and 8. Is it referring to the unbalanced system? Let me. Oh, okay, sorry. The example 8. Okay, example 8. Example 8. The balance system. Okay, example 8, balance system. Okay, this one. So right now, I'm showing to you right now example 8. Slide 5. Which one? Is it balanced or unbalanced? Okay, unbalanced. Okay, because I have also some requests. Okay, one request for Z line and also. Okay, so this one is actually we have, okay, for example, we have the three-phase system. Okay, and then in previous examples, what we do is actually we didn't consider impedance, line impedance. Okay, line impedance is referring to the impedance during the transmission. Okay, so between the generator and the load, so there will be what called some line impedance due to the inductance and also resistance of the cables. Okay, so in our previous examples, we haven't considered the line actually. Okay, so as you can see, this example 8 is actually, you set Z line is equal to 0. So when you set Z line, as can be shown here, is equal to 0. So actually, um, the solution is actually what you call is similar to what we have discussed. Okay, but when you introduce a Z line, okay, here, so your calculation will be very, very complicated. Okay, so for example, if the problem can only be solved by using y to delta or delta to y transformation, and after that consider a single phase equivalent circuit. Okay, but for this example, so since this is what you call, okay, so you need to convert this delta, because to have a single phase equivalent, the delta need to be converted into Y connection. So anything, the circuit in delta connection, you need to convert into Y connection. Okay, using delta to Y transformation. So for example, so this circuit shows that both circuit generator and the load are in delta. So we need to convert both in Y connection. So when you have convert into Y connection, it will become like this. Okay. Why we need to convert? Because right now, because we want to have what we call the neutral point, the reference node. Okay, and here. So for delta, there is no reference node. Okay, there is no reference that we can use. We have A, B, B, C, and C, A. There is no neutral point. So what we need to do is actually to convert into Y connection so that we have the neutral point. Okay, so when we have the neutral point, meaning that we have VAN, VBN, and also your VCN. So we have a single phase right now. We can obtain a single phase equivalent circuit. Okay, because we have already obtained the phase voltage, the phase current, and so on. Okay, so after you have converted this, you obtain the phase voltage and so on, and then also for the load. Okay, right now the load is actually, we consider this is actually phase impedance. Okay, because we refer to the neutral point here. Okay, so this one is actually, as you can see, we have VAN. So the voltage across this is actually VAN. So we can represent these three phase. Since this is a balanced system, so we analyze the system in single phase equivalent circuit. So this is your equivalent circuit. Okay. So after that, you can just use what you call a simple AC circuit analysis. Okay, you have a single phase voltage, you have impedance Z line and your Z load. Then you can calculate your phase and your voltage load. So this is the IA here, and your V is actually a phase values, voltage, phase voltage, and also phase current. Okay, so I hope I actually explain why. So Z line is actually the impedance of the transmission line. Okay, what you need to do when you have a delta, you cannot simply use what we have done earlier. Okay, you need to convert into Y connection. Okay, and then obtain the phase values. Okay, and then you proceed with a single phase equivalent circuit analysis. Okay, so all these values are actually in a phase parameters. Okay, then Okay. Okay. I hope that answer your question. Okay, so we go for the unbalanced system. So okay, unbalanced system. Okay. So I need to open up the notes for the unbalanced system. Yes, for only for delta, because we want to have the neutral point. Okay, we want to have a what is the VAN and then the load phase and so on. Usually for the load, okay, for example here, because the load right now, this is your line load, ZA. So we need to have the load impedance, phase impedance, okay, that referring to a neutral point. So ZA is not a phase impedance. So we need to have ZAN. So delta, you need to convert into Y connection. So that's we have ZAN. Okay, only for Y connection. Okay. For Y connection without neutral point, we can use mesh analysis to find out. Yes, you are correct. Yes, correct. But if you are using mesh analysis, okay, for example, this one, you are using mesh, okay, without neutral point, without neutral line, okay, without neutral line. So meaning that you don't have neutral line, so you can use mesh analysis. So you have I1 and also you have I2. Yes, possible. You can also use mesh analysis to obtain the values of the current and so on. Okay, but since this is balanced system, so balanced system meaning that all the values is balanced for all phases. So we can, since this is balanced, so we simplified it to be a single phase. Okay, so our analysis will be based on single phase. Okay, let me open the unbalanced system. So right now, I'm showing to you the unbalanced three-phase and load power calculation. Okay. So for unbalanced system, as you can see here, we have for each phase, okay, we have different load values. So meaning that you are not allowed to use the relationship between V phase and V line and I phase and I line. Okay, you need to manually calculate it. Okay, for example, for this delta connection, okay, IAB is this one. This is your IAB. This one is your IBC. And this one is your ICA. Okay, so to calculate IAB is actually you come from VAB here. So your VAB. VAB over your, this one is your ZA. Okay, then IBC and so on. So, and then after you obtain these values, okay, calculate IA. So this IA is your I line. So for the balance system, you can just use I line is equals to square root I phase, right? And then angle negative 30. But for unbalanced system, you cannot use this relationship. You need to manually calculate your line current based on the KCL note here. So we know that IAB is actually, okay, IA is actually equals is actually plus ICA, and this one is equals to IAB, and so on. So you need to use this information to calculate all your line current. Same case when you have the delta Y connection and so on. Okay, so as you can see here, we have three-phase four-wire system. So we have phase A, phase B, and phase C, and we have the neutral cable here. The neutral cable, as mentioned in my pre-recorded video, is actually just what you call a path for the current. Okay, so as you can see, this is an unbalanced system, meaning that all for the unbalanced system, there will be a current that flow inside this neutral cable. Okay, for the balanced system, IN will be always 0. Okay, so example slide 5. Okay, example 1, is it? Given an unbalanced delta connected load, which is ZAB, okay, supply voltage 110 volt per phase, positive sequence, and VAB as a reference. This one, unbalanced, example 2. Okay, this one, right? Is it this one? Oh, no. Example 1. Is it example 1? Okay. Example 1. Oh, tak ada. Example 1 is actually, I have already discussed in the pre-recorded video. For those who ask me, for example, for slide 5, example 1. Okay. For this one, example 1 here, I have already discussed in the pre-recorded video. Okay. This is straightforward. I only share with you example number 2. Okay. Example number 2. Example number 2, I have already upload in the e-learning. Okay, we go back to example 2, balance system. Should be, okay, hold on. Example 2, balance system. Okay, there is a question from your friend. For example, balance 2, V phase should be 120 degrees. Not 144. 2208. Okay, cool. Thank you very much. So how can I get 144? Yes, you're correct. So this one is not this one not 144. Okay, so this one is actually 120. So just okay. So this is example 2. So just 120. Thank you very much. Okay, 120. Okay, Any other else for the balance? Unbalanced. So unbalanced is actually quite um, straightforward, but okay, this one, do you understand this one? Example 4. Okay. So this one you need to know to read the phasor diagram. Okay. So this is unbalanced system. So meaning that the current values and also the angle is actually not equals. And I assume that since this has didn't mention about RMS or V phase or V line, so I just assume that the value is actually V phase, okay? V phase maximum. So as you can see here, this is to make some what you call to understand the question. So I usually draw, okay? I usually draw it, okay? So this is actually three-phase four-wire system. Okay, so actually the information, this is the important information, this one, which is you need to obtain it from the phasor diagram. After you obtain this one, so it is just a straightforward. Okay. Okay. So for unbalanced system, no questions? Okay, so for the example 6, which is a three-phase power, so I think that one also straightforward questions. Okay, just I want to remind to you that, okay, for this three-phase system, okay, for three-phase system, we know that P is 3 multiplied with V phase I phase cos theta V minus theta I. Okay, and this one is actually referring to the phase, the angle of the V phase and the angle of the current phase. Okay, and based on the note also, you can see that instead of using phase parameters, you can also write down your power three phase using V line, which is the equation is square root 3 V line I line. So this one is actually V phase RMS, okay? RMS. All are actually RMS. Cos theta V minus theta I. So usually the student will always confuse, okay? What is actually the values of the angle? Is it use V line or V phase? Because for the first equation here, since this is V phase and I phase, so it is logically you use V phase and I phase angle. But for the second equation, since we are converting V phase and I phase using V line and I line, so is it the angle of the voltage and the current is actually phase or line? So actually for this one, you need to remember that the voltage here, angle of the voltage should be referring to the angle of the phase voltage and also the angle for the I phase also. Okay, so the angle is remain the same, which is referring to the difference between V phase and I phase. Okay, I think that one is the thing that I want to highlight. Okay. Okay, so
Doctor,
yeah,
so if we use line angle instead of phase, we get the wrong answer?
yes, you will got
Oh,
the wrong answer.
okay.
Hmm. So you need to make sure that if you are using this one, the only one actually this parameters only lah yang bertukar, change. But the phase, the angle should referring to the phase voltage and phase current. Okay. Okay. And then we go to the. So this one you can refer. Okay, I have already uploaded in the e-learning. Okay. And actually, the power factors, okay, this one, the total power factor, you can referring also directly to the impedance angle, because we know that theta z is actually theta v minus theta I, and usually this one is actually referring to the impedance phase. So this one is V phase and this one is I phase. So you can use directly the impedance phase punya angle. Okay. Okay, next we go for the 2 watt meter. So actually the 2 watt meter is quite long if you refer the discussion of the why we can use only 2 watt meter to read the 3-phase power. Okay, usually for 3-phase you need to have every phase with a watt meter and then you just sum up. Okay, but there are some specialty where for the load that connected or the system 3-phase that is actually in Y connection, we can reduce the numbers of watt meter from 3 to 2. Okay, so that's why we are trying why and how to use these 2 watt meters. So actually the discussion is quite long if you refer to the textbook. So if you refer to the notes, so I just simplify. Okay, just simplify. So I think in my pre-recorded video, I have also explained why we need to have the formula. Okay, because for example, this one. So in my slide, I just conclude. Okay, so we have two only watt meter reading, P1 and P2. So I just conclude that P1, this is the equations. And P2, this is the equations. Okay, so it's quite long to discuss here because it involves the phases and so on. So if you are interested, I have already explained to you, I think, in the pre-recorded video. It's quite long actually. Okay, so but in your syllabus, I think is actually appropriate just to only know that to the watt meter number 1 is actually equals to theta, which is this one. Theta is actually your power factors. Okay, theta v minus theta I plus 30 degrees, and for the P2 is actually theta minus 30 degrees. Okay. Yes. You just need to memorize the formula. Because it's quite long. If you refer to the textbook, Sadiku, Alexander and Sadiku, it has actually discussed about this thing. Okay. So actually, for this example, so what I do is actually, as you can see, the total power. So I calculate the total power, okay, by using this formula, okay, 11.676, okay. And then the last question, asking the reading of 2 watt meters. So what is the P1 and what is your P2? So your P1 reading based on these equations, it will give you these values, while for P2, it will give you these values. So if I sum up P1 plus P2, it will give actually the same answer. Okay. So as you can see, the placement of the watt meter, and you only use only 2 watt meter. Okay. Actually, the common point here, as for the example, is actually phase B is selected as a common point, but actually it's up to you. You can place it the watt meter in any phases, and for the common point you can choose phase A as a common point. So it's actually not a problem. But for this example, it's use phase B as the common point. Okay, so if there are any questions regarding the three phase, example 7 and 9. What do you mean example 7 and 9 referring to unbalanced? Example 7 and 9 for the unbalanced. Let me see. Example 7 and 9. Okay, example 7 and 9. So example 7, no, because it's actually quite similar to example 6. And since there is no answer, so it's quite difficult for me also to do it. Okay, so you can refer to actually, I will give you one example. Okay, because this example 7, so we don't have the answer, right? So I will give you the one example from the textbook that you can, because textbook they got the answer, so meaning that the methods and so on, so you can check, double check kan. Kalau example 7 ni jawapan tak ada, so susah jugalah, whether sometimes maybe I also made some mistakes. Okay, so I will share to you all on the examples from the textbook, okay, with the answer. Okay, for example 7, and for example 9, no. So I haven't done that. Okay, this one is actually referring, why my, okay, this one is also actually referring, this is no problem. I can do it the solution for you. Okay, so actually my approach is I do the solution, but as always, the student can use it as a reference, but try to do it first. Okay, then if you stuck, then you can refer to my solution. Okay, because it will drive you to do more exercise, because yeah, I'm actually from UTM, so undergraduates from UTM. So during my study, so we don't have this what you call, the example is quite a lot, but there is no answer, so it will make it actually what you call do not encourage the students to do, because there is no answer. At least you provide the answer, then the student know whether it's correct or not, right? So that's why I'm trying my best to have the solution for you, so that you can use it as a reference. Okay, I hope so. And your test 1 result will actually reflect whether my methods of teaching is good or not good. Okay. If there is no question, then I think we can conclude our class by today. For today class, so meaning that we have already completed the topic 1, which is AC power. So starting today, we will concentrate on topic 2, which is the magnetization, the magnetic system, where this magnetic system is actually fundamental for all electrical appliances, such usually, especially for the electrical motors and also the electrical transformers. Okay, so I have pre-recorded the videos, so you can proceed after this to watch the videos. Okay, so there in the video is just what you call a briefing on the what you call the Faraday's law, Lenz's law, and so on. So, but do not what you call uh, emphasize on that. Okay, the main emphasis for this topic 2, electromagnetic or magnetic, is actually on the electrical circuit equivalence. Okay, so we have the magnet, so we can actually represent the circuit, the magnet, into an electrical circuit. Okay, so right now, when after you watch that, you will see that right now for the electrical magnet circuit, the current is actually represented by the flux. Okay, represented by the flux, and the resistance is represented by the materials of the core magnet. So please look at that. Okay, and then there will be a series parallel circuit. So how can you actually uh, show that that circuit is actually series, the circuit is actually parallel, and then you need to apply the basic Ohm's law to the magnetic circuit. Okay, so actually the same theory applied. Okay, basic Ohm's law applied, but it may be some what you call some hiccup there and so there, because we didn't familiar with the flux and so on. Okay, so please watch the videos, where there are 3 videos there. Okay, all actually about the fundamental of the magnetic and also the electrical, the circuit of the magnet that represent the equivalent circuit that represent the magnet. Okay, so we meet again on our next class on Wednesday on the discussion of the topic 2, which is the magnet. Okay, so thank you very much. Assalamualaikum and have a very good day.
Okay, Doktor.
Thank you, Doctor.